Perfect.
Okay, let's start the afternoon session. Our first speaker is Hiroyuki Fuji from Tsinghua University, called Superpolynomial Super-A-polynomial.
First of all, I'd like to thank the organizers for inviting me to this Geneva conference in 2014. And in my talk, I'd like to introduce my work in collaboration with Hidetoshi Awata, Sergei Gukov, Piotr Sulkowski, and Marko Stosic 2 years ago. And the main focus of my talk is string theory and quantum knot invariance and its categorization. So to discuss about such aspects, let me briefly overview how we can theoretical physicists are considering the quantum knot invariance. Yes. Yeah. The string theory is a physical theory that is defined on the 10-dimensional manifold. And choosing such 10-dimensional manifold in various ways, then we can find the low-dimensional quantum field theory that is realized inside this 10-dimensional manifold. And in my talk, I'd like to choose such a 10-dimensional manifold as a product space of 4-dimensional manifold and 6-dimensional manifold. And in particular, we will choose the 4-dimensional manifold as the Minkowski space of W4 equals to R13. That is named as Minkowski space. On the other hand, for the 6-dimensional manifold side, we will choose the manifold as a calculable 3-fold. And choosing in such a way, we can find the extended supersymmetric system on the 4-dimensional spacetime and the field string theory side. But here we are, my focus is a quantum knot invariance. And so to describe such a quantum knot invariant, then we should realize the 3-dimensional manifold. In particular, we will choose such a manifold as 3-sphere. And so to realize such a geometric situation, then we will choose the calculable 3-fold to be the special calculable 3-fold that is nothing but the cotangent value over S3. So this is our starting point, and from the starting point, I'd like to discuss how we consider such a quantum knot invariant from the string theory point of view. And as for the starting point, I'd like to mainly focus on the 6-dimensional manifold side, this manifold side in the string theory. And actually, if we consider the 6-dimensional manifold, we are able to consider the simple string theory that is so-called as topological M model. The topological M model is defined on the 6-dimensional manifold, and here we choose such a manifold as T star S3. And such a manifold is sketched in such a way. Oh, I have written too much. So, slightly smaller, then we can sketch such a 6-dimensional manifold like this way. And this is the T star S3. And in this manifold, we can find the compact Lagrange manifold S3 right here. And in the string theory, we can introduce the higher dimensional object that is so-called as D-brane. The D-brane in the topological M model should wrap around the Lagrange manifold inside here. And here we choose here we will introduce the n Lagrangian D-branes wrapping around this S3. So on this submanifold, we can realize the low-dimensional TQT that is nothing but the SUN Chern-Simon gauge theory R3. But here we are rather interested in the knot invariant. So to realize the knot diagram inside this geometry, we will introduce the knot diagram like this way. And as a boundary point, as a Lagrange submanifold, non-compact Lagrange submanifold, we will introduce the LK like this one. And this LK and S3 are intersecting along the knot diagram. So, in such a way, we can realize the knot diagram inside this calculable geometry. And actually, this is also the Lagrangian sum-manifold. Then we can introduce yet another difference right here. So this is the geometric setup we want to first study about the not invariant. And
could you explain D-brane again?
D-brane is a higher dimensional object, and actually on this D-brane, the open string can take an n. And actually, such a degrees of freedom gives rise to the gauge degree of freedom.
No, but in this example, what is D? It's three-dimensional, or
This is a three-dimensional because this is a topological.
yeah, no, but you wrote D-brane, but this is a three-brane. I mean, it's just wrapping 3 times. It's not higher dimensional. It's the same dimension. I don't know.
I will explain about the ordinary D-brane in the type 2A superspace.
No, but in your example,
In this case,
what is the dimension? It's 3 still.
Yes, this is 3.
So it's not higher dimension. It's simply wrapping several times, but it's not higher dimension.
Absolutely.
Okay.
Yeah.
Just
And later,
yeah.
okay, yes.
And can you define LK?
Fk is the Lagrangian sum-manifold inside this calculable geometry.
But I have many possibilities, or?
I think if we specify the Mock diagram, then we can construct it in a one way. And actually, in the case of the torus knot, such a construction is manifestly done by Taubes and et al. And in such a kind of algebraic knot case, then we can construct the LK very manifestly.
So, LK is the conormal boundary, isn't it?
Yes. In the language of the knot contact homology, they say so. Yeah.
What is the interpretation of n? It's
N is the number of
wrapping n times around.
No,
the
number of
thing,
difference.
or
Number of degrees.
number of
Yes. So this is the geometric setup, and we want to calculate the physical quantity.
Cover.
The physical quantity we want to calculate is a partition function. And in the case of the string theory, the partition function could be calculated by counting the number of homomorphically embedded open Riemann surfaces into this calculable geometry. And in particular, in this case, there are 2 kinds of Lagrangian D-branes. So we can count the number of Riemann surfaces that have the ending points on the LK and S3, connecting these to some manifold like this one. And such a number of homomorphically embedding maps causes the some generating function. And such a generating function is so called as the string partition function, topological string partition function. And essentially this is defined by X6 information of the coordinate bundle and S3 Lagrangian sum-manifold and LK. And essentially this function is parameterized by H bar, that is so called as string coupling constant. Essentially, this coupling constant counts the Euler number of this open Riemann surface. And the explanation this H bar, like this way, then we will introduce the Q parameter, like this. So, in such a way, we can consider the generating function of the number of homomorphic embedding maps, and this is so called as the open string partition function. And actually, from the by using the Chern-Simon gauge theory interpretation, then this topological string partition function could be identified with the quantum not invariant for not diagonal K associated to UQ SLM representations. And the Mises representations are depending on the number of difference wrapping around this Lagrangian sum-manifold. So this is a story about the string theory, how string theories are considering the quantum not invariant as a string theory.
What is the angle on the
Yes, this I have not manifestly written, but inside this Lagrangian sum-manifold, the n difference are wrapping there. So associated to this this number of difference. Yes, if we should express such a degrees of freedom more manifestly, then we should introduce more matrices that is expressed as the Wilson loops. And there are 2 kinds of Wilson loops associated to this S3 and LK. And such 2 kinds of Wilson loops are unified into the so-called as a Ogilvy operator. And using such operator, then we can manifestly realize such kind of open string partition function. But unfortunately, I don't have time, so I'd like to skip such a detail.
Could you write a definition for that open string partition?
I think that okay. I'd like to show you the next vantage point because in this picture it is not so easy to write down very manifestly, and I need to introduce a lot of things to do that. But going to the next picture, then we can write down very simply. So
for a single brain, the theory is trivial?
single D brain, which
Yeah.
D brain?
Yeah.
In this case,
And
U1 theory, you mean? U1 average
S-
average
one.
Isn't
chance.
that
Yeah.
like J1? Is,
SU1.
yeah,
No, U1.
it's
U1.
the group. It's
Yeah, actually
It's
U1.
not
So
trivial.
this is
it is
U1 part could be decoupled from this system.
I see.
So
So a single brain does nothing. You need at least two brains.
single brain, we consider that this should be a U1 chance-time case theory. Yeah.
It's my fault. I just got a single thing.
So this is the sketch of the theory, but actually speaking, this different system is not so easy because we have to be careful about the intersection of complicated form of the Lagrangian difference. And actually it is not so easy to calculate directly from this geometry. So, to resolve this point, we will simplify this geometry by the string duality. The string duality today I like to employ is the conical transition. The conical transition is one of the string duality, and this involves the topology change of the six-dimensional manifold. And I'd like to sketch such a transition briefly. Here I'd like to denote this geometry like a simple form, S3 and S2. And actually this is the radial direction of this non-compact Calabi-Yau three-fold, and taking a slice of the constant radius, then we will find S2 times S3 geometry for this case. And on the top of the S3, we have introduced ND branes right here. So this is the geometric setup that corresponds to the SUM chance-time gauge theory. But this size of S3 is not sensitive to this topological open string partition function because this is a topological invariant. So we can deform this geometry by shrinking this size of S3 and growing up this S2. Then we will find the different topology right this way. In this case, S2 has a non-trivial volume at the top of this locus. And more geometrically speaking, this is nothing but the exceptional P1 that is found from the growing up of this geometry. So, if we go to this geometry, then we can count such kind of number of homomorphically embedded open Riemann surface rather easily. Because this geometry is nothing but a toric geometry that is given as O-1 plus O-1 bundle over P1. And in this case, we can describe the partition function in the point form. In this case, in the right-hand side, Z dot open and X6 prime, and corresponding to this Lagrangian sum manifold, then we can find the Lagrangian sum manifold inside this toric Calabi-Yau geometry. And so here we want to count the number of homomorphic disks. Essentially, we want to count the number of open Riemann surfaces embedded into this Calabi-Yau geometry. And in this Calabi-Yau geometry, we will find the Lagrangian sum manifold inside here, and such open Riemann surfaces are ending on this K prime and homomorphically embedded into this X6 prime geometry. So in this case, the homomorphic embedding map F is labeled by two kinds of parameters, winding number and rubbing number. For example, if we consider the bulk geometry in sigma GH, then pushing forward by this homomorphic embedding map, then these open Riemann surfaces are embedded into some two cycle inside this geometry. But we restricted that this homomorphically embedded open Riemann surface must have the boundary on the Lagrangian sum manifold. Then this should be the element of the negative homology class of this there is only one exceptional cycle here. So this H2 is only it is isomorphic to Z, like this way. So and this wrapping number, beta is a wrapping number. So this characterizes the homomorphic embedding map in this way. And furthermore, the boundary component C1 to CH are also embedded by this homomorphic embedding map. And each of CI's are embedded into the first homology class of the Lagrangian submanifold. So in this case, this is also isomorphic to Z, and this WI number means the wrapping number of this embedding map. So in such a way, this homomorphic embedding map is labeled by two kinds of parameters. And using this parameter, then we can find the open string partition function in the following way.
This LK prime, should this be singular now?
Sorry, OK prime.
LK prime. So LK has this, there was this knot in S3, but the
Yes.
S3 gets collapsed.
Yeah, and drawing that after
Blowing
drawing up,
to S2. So are you saying that LK prime would then still be smooth under this transition?
I think so. Yeah, and actually in the case, manifest construction is not only for the torus node, but we expect that such kind of smooth Lagrangian submanifolds should also exist in such for
see.
general.
So you don't know. I was going to ask also how you don't know that they exist, this LK prime. I also want to ask where they come from, so it's a little conjectural for a general knot.
Yes, just for general, it is
No,
conjecture.
but Cliff Towers has a construction of such a Lagrangian.
After this transition, on the other
Yes,
side, not
yes,
the
which
LK,
is
but the
supposed
LK
to
prime.
be, yes, mathematically defined Lagrangian.
Okay, thank you very much.
In this thing, not in T squared S3, but in this one.
-1 and O
Okay.
-1, yes.
Okay, so using these two labels, then the homomorphic embedding maps are number of homomorphic embedding maps are labeled by W1 to WH that counts a wrapping number, widening number of the boundary. And this is the bulk part of the Riemann surfaces are also wrapping around the relative 2 cycle. Then the genus G Riemann surfaces are number of the homomorphic embedding maps are labeled in such a way. And such a number is so-called as the open longitude invariant. And as a generating function defined in such a way,
So these are rational numbers now.
rational, yes, absolutely. I should say so. And actually, this rational number, this is the rational number because we have to be careful about the multiple cover formula. So if we take it into such a kind of things, then we can extract the integer from this open longitude invariant. And this is a generating function that is given by 2g minus 2 plus h. And this is summed over g and g greater than 0 and h greater than 1. And this is weighted by a to beta and trace b to w1 to trace b to wh. Here b is the matrix that has the diagonal elements like this way. And this parameter is so-called as the open string moduli. And so this is so-called as the open string free energy. And exponentiating this free energy, then we find the open string partition function on this geometry. Essentially, this is labeled by A, Q, and B. Yeah. This is equals to exponential. Yeah. So in such a way, we can count if we can count the number of homomorphically embedded open Riemann surfaces into this Calabrese geometry, then we can extract the open string partition function in such a way. B is only an infinite rank matrix, and whose elements are diagonals are given as x1, x2, and so on. So, and furthermore, there is a beautiful structure about this one, because these traces are seen as a sure function of the fundamental representation, and its elements are x1wh, x2wh, and so on and so forth. So using the Frobenius formula or the Schur function, then we can rewrite this topological string theory partition function as in the following form. Frobenius formula. Then we can expand this top open partition function into the following form. Yes. Here, R means the GL infinity irreducible representation. And essentially, this is labeled by Young tableau. And this is a Schur function, and all of the dependence of B here is summarized into this Schur function part. And we can find the coefficient that purely depends on A and Q like this way. And at this point, we can find the following conjecture. The conjecture is claimed by Oguri buffer and Lavastido-Marino and buffer. The claim is that Oguri buffer and Lavastido-Marino buffer. The claim is that this partition function is related to the current HOMFLY polynomial. And taking into account of the appropriate normalization factor, that is, the current HOMFLY polynomial is equals to 1 for the case of analogue, then correspondingly, we will introduce the following normalization. Here, this O means the analogue. So, this is a conjecture proposed by Oguri buffer and Lavastido-Marino buffer. And actually, using this formula, then we can realize the quantum knot invariant given the current HOMFLY polynomial by counting the number of homomorphically embedded open Riemann surfaces into this geometry. So this is a famous story about the connection between the string theory and the quantum knot invariance. But this is a story about the 6-dimensional manifold side. Namely, we have used only the topological A model. But this is the topological A model, and this topological A model should be embedded into the type 2S superstring theory that is defined on the 10-dimensional manifold. So going to the 10-dimensional manifold side, we can find the new aspects of this topological invariant.
Excuse me.
Yes?
Where is the information of large N?
Large N, okay, that's a good question. A is chosen to be Q to N. Then this is the assumption of the geometric transition. I have forgotten to mention that. Thank you very much. Yeah. So let us go to the type 2S superstring theory picture. And this string theory is defined on the 10-dimensional manifold, as I mentioned in the starting point. And in this case here, we choose the 10-dimensional manifold M10 prime as the product space R13 times X6 prime, the root 24 in this case. And in this geometry, we have introduced the T-branes wrapping on the Lagrangian manifold. This is denoted like this one. But in the type 2S superstring theory picture, we will choose the D-brane to be the 5-dimensional object that is so-called as the 4 branes. And the 4 brane has a 5-dimensional world volume. So this is the 6th 3-dimension part. So there remains the 2 dimensions. And 2 dimensions are chosen to be filling the codimension 2 vectors in the Minkowski space, our universe. And on this manifold Minkowski space, we can define the 4-dimensional quantum field theory. And in this picture, such a D4 brane could be seen as a surface operator that describes the defect of the 2-dimensional defect in the 4-dimensional gauge theory. So this is a situation setup that corresponds to the topological string theory. And about this setup, the following conjecture was also claimed by Oguri-Buffer and Damasceno-Marino and Buffer's paper. And their claim is that the dr x6 prime nk prime aq is given by the BPS index. And this BPS index can be found by counting the number of BPS states. And in the string theory language, these BPS states are created as the D2 and D0 brane bound states. So this is a new physical picture about the quantum dot invariant. And actually there are a lot of undefined things have been introduced. And one of them is the BPS states. The BPS states is the special quantum states that is annihilated by the half set of the supersymmetric generators. Such a BPS states is denoted as BPS, then by the half set of the supersymmetric generator kills this state. So this is the abstract definition of the BPS states. And Oguri-Buffer and Damasceno-Buffer says that such a BPS states could be realized as a D2 and D0 brane bound states. And such a different configuration could be understood inside this geometry as follows. Firstly, we consider the D2 branes. D2 brane is a three-dimensional object in the string theory. And this D2 brane can graph around the second homology class, but this should be the second relative homology class of this, ending on this D4 branes. But this is a three-dimensional object, so there remains a one-dimensional part. And such a one-dimensional part is chosen as a time direction in the Minkowski space. So this is a D2 brane configuration. But if we introduce the further D0 brane to this system, then we can construct such a kind of BPS states. And D0 brane is a one-dimensional object in the type 2A superstring theory. So in this case, this particle is extending also to the time direction of the Minkowski space and point-like object in the Calabi-Yau direction. So this is a D2 and D0 brane bound states that the Oguri-Buffer and Damasceno-Marino buffer claims. And from this configuration, we can find such kind of BPS states that is killed by the half set of a supersymmetric generator.
Can you finish the definition? What is D2 divided by or slash zero?
D2
and what is bound? Sorry?
D2 and D0. D2 and
Just a
D0 are
combination.
stacking. Sorry?
And what do you mean by bound? I mean, what do you mean of made of?
This is not
Yeah.
divided. D2,
Yes.
D0.
And what does made of mean and what does bound mean?
Bound means that this is a physical sense, but for example, if we consider the D2 brane is wrapping around the relative 2 cycle in such a way, then the D0 brane is localized on this D0 brane, D2 brane. This is a D2 inside the Calabi-Yau direction, and this vertices means the D0 brane locus. So this is a brane setup I want to say. And actually, okay, I should say more than, but I just go further. Anyway, this is the BPS states and in the realization of the string theory language. And this BPS states spans some vector space that is so-called as Hilbert space, BPS Hilbert space.
May I just ask in these numbers that you're using, D4 and so on, you don't count space directions or something? How do you count
Space direction, yes. D4 brain has five-dimensional object. So 4 plus 1.
Oh, it's always 1 plus 1.
Yeah, plus 1. So this is this 3-dimensional, this is 1-dimensional. Yeah. And this BPS state spans the BPS Hilbert space and all of the BPS states are living inside this vector space. And actually, this vector space is a graded vector space. And physically, such a grading could be realized as a quantum number of this BPS states. And actually, in this setup, we can find 3 kinds of quantum numbers that the BPS states have. Quantum numbers. BPS states. The first one is so-called as the D2 brain charge. Essentially, this is labeled by wrapping number beta of this relative homology class. And this is integer. And the second one is so-called as the D0 brain charge. And this could be found by counting the point-like object inside this Calabi-Yau geometry. So this is only the number of D0 brains. And we label this one as n, small n. And third kind of quantum number is so-called as spins. Essentially, we are considering the quantum field theory. And after seeing this brain configuration, we can find that D2 and D0 brains are filling the one-dimensional side inside the Minkowski space. And such a one-dimensional object could be understood as a particle's trajectory after the time evolution. So this such a BPS state is nothing but a BPS particle state. And such a BPS particle, usually in the quantum mechanics and the quantum field theory, all of the particles have non-trivial spins. And spin is nothing but the isometric representation of the isometric group action on this Minkowski space. And in general, this should be the SO4 or SU2 times SU2. But actually speaking, in this case, corresponding to the introduction of the knot diagram, then we have introduced a codimension 2 object inside this Calabi-Yau geometry. So such an SU2 times SU2 isometric group, spin symmetry, is broken to the subgroup of SU2. And its dimension is nothing but the spin charge. And in general, in the physics notation, this is described by introducing spin parameter J that takes a half integral value.
Excuse me.
Yes, please.
Is the number of D0 brains a natural number or an integer?
Yes, that's a good question. At this level, we choose that as our natural number.
Okay.
Yeah.
Natural.
Yeah, but depending on the grading shift, we can take the t to be a negative one. But this is only a grading shift.
So essentially natural number.
Essentially, this is natural number.
What's the relation between BPS invariant and the Donaldson-Thomas invariant?
This is a good question. And if we consider the U1 gauge theory on the U1 gauge theory on the 6-dimensional micro side, then we can also consider the quantum field theory living on the 6 dimensions. And in the sense of physically, in the sense of the 6-dimensional QFT, then we can count the instant numbers. And such an instant number is nothing but the Donaldson-Thomas invariant. And physicists are believing that such a Donaldson-Thomas invariants are also equals to the BPS number and the Gromov-Witten numbers.
So this is the non-Newtonian generalization of Donaldson-Thomas?
In this case, I think not so, because in the 6-dimensional side, I have not introduced such kind of things. Instead, that I have introduced only D4 brains. So there is a non-trivial D0, D2, D4, and D6 bound states we should count. And I think the setup we are now considering should be only the U1 gauge theory.
And another question on language. Would you say that a D4 brain is a 5 brain or not?
Five brains are 2B string theory, type 2B superstring theory.
I see.
Or if we uplift this theory to the M theory, then such a D4 brain could be unified as an M5 brain.
Okay.
Yeah.
Thank you.
And I think the Witten's NS5 should be the TDO configuration of this situation. All right, good. So now let consider such a grading structure. We have introduced the 3 gradings for this BPS Hilbert space. So this is a graded Hilbert space, graded vector space. And on the graded vector space, we can compute the BPS index in the following form. The BPS index is a trace over the BPS Hilbert space that is defined on 60 million manifold with Lagrange sum manifold. And this trace is weighted by the point formula. Firstly, we will weight by the spin degree of freedom. This is also the fermion number of this BPS states. And we also introduce the A parameter weighted by beta. And we also introduce corresponding to the Q corresponding to D0 brane charge. Then we introduce Q parameter right here. So this quantity is so-called as a BPS index. More manifestly speaking, this is written as the following quantity. Beta n on J is summed with the weight Q2 plus 1, A to beta, and Q to n, and this is weighted by rank of the BPS Hilbert space. And we restrict the special sector that is specified by beta n and J. Yeah. So in such a way, BPS state could be calculated in such a manner.
But that, well, only if it's finite. If these dimensions are finite, do you know that?
Finite dimension Hilbert space, BPS Hilbert space?
No, I mean you've introduced 3 quantum numbers, actually just 2 because you're not using J except up to sign. And now you're telling us that you believe that if you fix 2 of the quantum numbers beta and n, that piece is finite dimensional. Otherwise this doesn't make sense.
Yes.
So do you know that?
If you fix the beta and n.
If you fix beta and n, do you know it's finite dimensional? I mean otherwise this doesn't make any sense. Is that a theorem or just a guess? Or?
Experiment. Experimentally we can check it. Yeah, because in the special situation we can calculate this BPS index very explicitly. In particular for the case of the torus node, we can calculate this number. And from this experiment, then we can confirm that such a situation should hold. But in general, I don't know. This is a conjecture.
So that implies also that J is bounded by n and beta. So do you know how big this SU2
Sorry, I don't know.
can be? Because otherwise it again would be infinite.
Yes, so I know theoretical physics, so experiment is everything.
Okay.
So
no, experiments are fine. I like experiments. But
this is my Higgs.
So if J is bounded, do you know what it's bounded by? The size of this SU2 representation.
Essentially, this is not bounded.
It has to be bounded, otherwise your sum is meaningless.
No, all of the value.
No, J. If you fix beta and n,
fix beta.
then J must be bounded because you have a sum with an integer.
I agree.
So it wouldn't converge. So there must be a maximum. Do you see the reason? I mean, I don't know why this. Maybe somebody.
I should start.
Okay.
So the boundedness of J comes from if you compute the modular space of this
Yeah.
object. So you can think about the BPS object as some sheaf, and then what you're looking at is a modular space of this sheaf under a certain stability condition. And then the spin would be some sort of homology of this modular space.
Oh, I see.
Thank you very much.
Also, I have a related question. How should we think of the BPS Hilbert space, like some sort of geometry quantization of some modular space of elliptic equations, right?
Actually, such kind
of L square harmonic forms on modular spaces is that BPS Hilbert spaces is geometric.
geometric construction of BPS states, BPS Hilbert space is not so easy problem, I think. Then only the analogue case it is constructed. But this is the same story as you know in the case of the Jun30Mon and so on. But in general case, I don't know. Physically, such an existence of such BPS states, Hilbert space are proposed are only a conjecture, I think. Yeah.
And then, as he remarked, everything is homological. The BPS index is some sort of Poincare polynomial. Also.
Yeah. Yes. I will discuss such a kind of polynomial soon later.
Just a few words about that. Is it so that one can conjecture some kind of moduli space that it should be? I didn't understand which moduli space was being discussed.
Here in the case of the BPS Hilbert space, to define BPS Hilbert space, we discuss about the 4-dimensional QFT. Q4-dimensional QFT with the surface operator there. And on this modular space, we can construct the
which modular space?
ramified instant homology space. And this connection was proposed by Gukov-Horan's work. And actually, you believing this is still a conjecture, but actual construction, real construction could be done on this space. And actually, such a space is nothing but a affine normal space. So we can manifestly construct such a previous Hilbert space in some special cases.
And is it compact? And is, I mean, Gates group is compact or non-compact?
Compact.
Compact.
Yes.
Yes.
So now, I think I have so much used time, but our main claim of the Ogre buffer is that this BPS index should be equal to the R of X6 prime and AK prime AQ that is counted by, that is found by counting the homomorphic embedding map inside this Calabrian geometry. And seeing this relation, then this is a physical discussion, but seeing this relation from the knot theory side, this is nothing but the categorification of the quantum knot invariance. Namely, the dr is essentially related to the colored HOMFLY polynomial. And this is the two-parameter polynomial A and Q. And this polynomial, behind this polynomial, we can find the triply graded homology that is nothing but the BPS Hilbert space. And this is a general story about the categorification of the quantum knot invariance. Story, Sergei Gukov and Marko Stosic proposed the following conjecture. How much time do I have? Okay, 10 minutes, okay. Then the conjecture is that the Gukov Stosic claim that corresponding to the BPS Hilbert space, then we should find the nice triply graded homology that is so-called as a colored HOMFLY homology. And its existence is nothing but the conjecture by Sergei Gukov and Marko Stosic. And colored HOMFLY homology and colored HOMFLY polynomial is related by this relation. Yes. So this is a relation between the colored HOMFLY homology and colored HOMFLY polynomial. And they further claim that this triply graded homology itself should be the knot invariant, that is invariant under the Reidemeister rules. So if we believe that, then we can find the nice refinement of this quantum knot invariant. And this is nothing but a colored HOMFLY, colored superpolynomial. And colored superpolynomial is nothing but the Poincare polynomial of this triply graded homology. Namely, this is the three-parameter polynomial that is given by an I, Qj, Tk, rank of triply graded homology. Yeah. So in such a way, from the string theoretical point of view, then we can find the natural new three-parameter polynomial that is so-called as a colored superpolynomial. And there are a lot of interesting story and properties about the colored superpolynomial. And one of them is nothing but the D-module structure behind there. And such a D-module structure could be found if we restrict representation to be the completely symmetric representation. Namely, the n-1 box case, then we can find a nice structure. Actually, in this case, we can find a nice reduction of the colored superpolynomial to the colored Jones polynomial. Actually, choosing the A equals to Q squared and T equals to -1, then we can find that this polynomial reduces to the colored Jones polynomial. And behind the colored Jones polynomial, there is a beautiful story proposed by Kashaev and Hiroshi Murakami and Jun30Mon that is so-called as the volume conjecture. And essentially, this following conjecture discusses the asymptotic limit of this Carl-Jones polynomial by taking n equals to infinity and q equals to 1 by taking the double scaling. On the other hand, another beautiful story is the AJ conjecture proposed by Tande and Silvers Galufaridis. And this AJ conjecture claims the existence of the nice Q difference operator that annihilates the Carl-Jones polynomial. So this is an AJ conjecture, and from the physical viewpoint, these two conjectures could be naturally interpreted as a quantization of the SL2C Chang-Simon gauge theory. And from this point of view, Sergei Gukov has proposed the quantum Borel conjecture, and physically these two conjectures are very naturally interpreted as a semi-classical limit and Schrödinger equation of the quantum field theory. So this is a story behind the background of the Carl-Jones polynomial. And here we have natural two-parameter generalization of this Carl-Jones polynomial. So we want to study about such aspects, and from some experiments of the mathematical physics, then we can find the following conjecture. Here we tentatively call such conjecture as super-A-polynomial conjecture, framed by my work in collaboration with Gukov and Sulkowski. Oh. Yeah. The main claim is as follows. Let Pn K AQT be the current superpolynomial that whose representation is specialized to the completely symmetric representation like here. Oh, thank you. And for this polynomial, we can consider the following Q difference operator. That annihilates this current superpolynomial. Namely, I have super k x hat y hat AQT annihilates the three-parameter polynomial equals to 0. And this existence of such Q difference operator is nothing but the main claim of our conjecture. And actually, this A super is made of the x hat and y hat. And these x hat and y hats are nothing but the Qy operators that acting on this current superpolynomial. Namely, x hat acting on Pn, then Q to n is obtained as an eigenvalue. On the other hand, y hat is acting on Pn, then n is shifted by 1 unit. So, in such a sense, we can find that such a nice polynomial with respect to p hat, y hat, the finite order polynomial could be found as a Q difference operator that annihilates the current superpolynomial. So this is nothing but our conjecture. And actually, for some Swiss knots and torus knots, we can find such a manifest operator that annihilates this current superpolynomial. And from this observation,
why do you need the representation to be the special one?
Completely symmetric one.
I say, why do you need that one to be that special one?
To find the...
no, because there's an obvious generalization. I mean, the difference operator, the y hat, is relating n to n minus 1.
Absolutely.
But if n is really Sn, it's relating Young diagram, you take away the last square.
Yeah.
So if I have any Young diagram, you could just take away all of the last corners.
Yeah.
And that would be the natural analog of the difference operator. So I don't see any reason to specialize so much.
Okay.
Well, for another time. But
But I agree.
Just a remark, yeah.
One of the problems is that the current superpolynomial, actually speaking, the current superpolynomial is only defined for the rectangular representation in the sense of the Gukov-Stosic's definition. So, of course, if we use the string theory, then we can calculate the BPS index for any representation. But in the
So you don't know how to calculate if it's not a rectangle, or?
rectangular case,
can
there is a definition of the Gukov Stosic definition. This is an axiomatic definition
I see.
that relates with known homology, like a Hobano homology or Hobano homology. But other cases are not known.
I see.
So
But
this
then
is
of course
one
you
of the
can't do
problems.
the induction, yeah.
Yeah.
Okay.
I mean, really you should expect more variables, more xi s and y
Yes,
s.
higher dimensional
Well, that
character
also,
variety
that
should be
also,
found.
sure, yeah. But even to get the thing going, you have to be able to remove corners. So if it's only rectangles,
Okay.
you're in trouble.
So, so from this observation, we can define the super-A-polynomial. The super-A-polynomial is nothing but the semi-classical limit of this Q-difference operator. Namely, x hat and y hat are operators, but in the semi-classical limit, we can replace these two parameters, two operators, by ordinary commutative variables. And if, furthermore, here we choose q equals to 1 specialization, then we can find the two-parameter polynomial whose coefficients are determined by a and b. So this polynomial is so-called as a super-A-polynomial we have introduced. And actually, related to the HA conjecture, this super-A-polynomial is reduced to the ordinary A-polynomial that is associated to the SL2C holonomy representation. And this is taken by n equals to 1 and t equals to -1. On the other hand, if we only choose t equals to -1, namely the decategorification limit of the super-A-polynomial, then Minami-Yanagichi and Kamabapa found that this such a polynomial reduces to the augmentation polynomial of the not contact homology. And to find such kind of polynomial, we have to make a change of variables. But essentially, as a character variety, such a two varieties are known to be believed to be equivalent. So in such a way, the super-A-polynomial is related with a known polynomial. This is the A-polynomial, and this is the augmentation polynomial. And I think oh, time is up. Yeah,
Can you have a little more?
okay, I'm sorry, but I'd like to mention only small thing. If I end this one, then this is only observation. That I want to continue one more observation. This means that actually, going back to the second picture of the story, namely, we have counted the number of open velocity variants to find the HOMFLY polynomial. And in particular, focusing on this part, then we can define this free energy as a generating function of G 0 and 1 boundary number. This is the open velocity variant. And this is weighted by alpha, W, and Q to beta. And essentially, this could be calculated as a Hodge integral over the moduli space of G 0 and 1 boundary. This is defined on x6 prime and lk prime. And this is integrated over 1. And in the case of the torus knot, such a Hodge integral could be calculated directly. Such a formula is found by Diaconis, Shende, and Buffer. And such a rational number could be calculated as a localization computation. On the other hand, using the augmentation polynomial, such a quantity is beautifully found as the arbitrary map over the character variety that is defined by the augmentation polynomial. That is, namely, this beta of alpha is nothing but a solution of the augmentation polynomial parameterized by Q. And actually, you can expand this solution and by integrating alpha, then you can find a miraculous coincidence between the discrete Sandon number and the arbitrary map defined on this character variety. And this great statement is named as linear symmetry. And work by Akanagic, Eto, Mugu, and Baffa. And this is a beautiful story story, and we can also, starting from the super-A-polynomial, then we can define this story. Namely, starting from the super-A-polynomial, then we can find a nice refinement of the augmentation polynomial. Here we name such a polynomial as a refined augmentation polynomial. And by this refinement, we find the one parameter generalization of the Gromov-Witten invariant, and this is nothing but a refined Gromov-Witten potential. And by using our super-A polynomial, then we can find that this open Gromov-Witten invariant defined by t parameter, it takes a positive number for the torus ones. And furthermore, we can find a nice multiple cover formula for this one, and we can also extract the positive integer for the torus node case. And such aspects should be understood in more detail. And actually, in the story, the augmentation polynomial plays a role of the Gross-Zipper's slab function. So, in order to understand such aspects, in particular the linear symmetry, this is a very mysterious symmetry, but such a symmetry should be understood from the Gross-Zipper's viewpoint and reconstruct the Gross-Zipper data for this augmentation polynomial. But this is a speculation of my future plan. So thank you very much for your attention. Hyperbolic node case, yeah, actually we can calculate the 4-1 node. And this calculation is done by making use of the Gukov and Stosic work. They are assuming the axiomatic definition of the triply graded homology. Namely, they have proposed some spectral sequences connecting to the non-homology, like Hobanov homology, not-player homology, and Hobanov-Rozansky homology. And as an extrapolation of these these data, then we can find the we can determine uniquely the triply graded homology. Such a things could be done for the case of the figuring. But in the case of the topological string theory, actually it could not be done because this is related to a supersymmetry. Physical discussion, supersymmetry is broken in the case except for the torus case. So this is the point we have to resolve. And actually, in the case of the distinct standard, we can also consider the 4-1 node case. But in the case of the 4-1 node, we can also find an integer, but this positivity is broken down. So this should be related to such aspect, but I'm not sure. Yeah, this point should be explored in the future. Yeah.
Well, I just wanted to, if you could say something about the geometric interpretation of the variables in the augmentation polynomial. I mean, do you have such a thing, or? Yeah.
In the linear symmetric case, they believe that there should exist a nice Strominger-Zastrow mirror symmetry that connects the ordinary conifold geometry with this augmentation variety. Namely, adding the dw equals to augmentation variety, then such a B model Calabi-Yau could be defined.
Landau-Ginsburg.
Absolutely. Something like that. And actually, such a polynomial is nothing but a Gross-Zipper's slab function. So, but at this point is not so much studied. And actually, the Kamran and their collaborators are considering such aspects from the not contact homology viewpoint. So this point is not the other Strominger-Zastrow mirror symmetry. This point is still very mysterious and conjecture. But actually, such a kind of calculation could be done, and we can find a miraculous coincidence between them.
Okay, we should have our break now. Let's have 20 minutes break.